Hi, this is the presentation for our work, FastSR-NeRF, improving NeRF efficiency on consumer devices with a simple super resolution pipeline. First, NeRF has been a popular technique that creates many awesome applications, such as 330-degree views, virtual try-on, and thin fly-through. These applications have already influenced our daily life and changed the way people interact with computers. However, there is a challenge of the current NeRF pipeline, which is it often needs to be trained on powerful GPU before being used on the end user. This greatly limits the usage of NeRF and also raises privacy issues. In contrast, if an user can get to capture the data, train and deploy the NeRF model all on their own consumer devices, this will enable a much better use case for NeRF and enhance the privacy. In this work, we aim to improve NeRF training and rendering efficiency on consumer devices via super resolution. To understand NeRF performance bottleneck, we first look at the typical NeRF workflow. For the typical NeRF model, there are sparse features to represent the 3D space. With these features, to render a pixel, it will shoot a ray in the 3D space and sample points along the ray. For each point, it will use an NLP network to infer the color and density from the feature and view angle. Then you will compute the integral of the density and color along the ray and get the final color of one pixel. This process is called volume rendering. For the typical NeRF, to generate an image, you'll need to shoot thousands of rays and have millions of billions sampling points. This large amount of rays and points make the volume rendering slow and the performance bottleneck of NeRF. Among many methods to accelerate NeRF, super resolution is one of the most straightforward techniques that can improve NeRF speed. It is because with super resolution, we can let NeRF output at a lower resolution and super resolve the output to the desired resolution. In this way, the size of the 3D feature space are smaller and the number of rays and sampling points are also reduced. So the volume rendering process is highly accelerated as the computation amount is reduced. Furthermore, super rays are essentially CNN models, which are parameter efficient and already highly optimized for modern hardware, such as GPUs and commodity CPUs, thanks to the involvement of deep learning. Although super resolution is a promising way to speed up NeRF rendering, we observe that existing SR-based NeRF are expensive in training. This is because they either require extra data, such as depth or high-resolution reference images. Second, they rely on specialized SR model to take in the extra features. Therefore, the SR model must be trained from scratch. Third, they often require extensive training images, such as 10K extra images to train. This is due to the data-hungry nature of the CNN SR model. These extensive images are typically generated by the highly accurate teacher model, which make the training process super slow. In contrast, this work, we aim to use only RGB output from the NeRF at the low resolution. In this way, we can take any pre-existing SR model and even leverage the pre-trained model. And we also just use the standard images from the data sets. Okay, now let's take a look on how we achieve this. Here is the training pipeline of FastSR-NeRF. In the beginning, we utilize a technique we call random patch sampling to crop a patch from the training images. And then we fit this patch to the pipeline as we just described it. And then train on the L2 losses on the output and the ground truth high resolution images in an end-to-end manner. As you can see, we only modify the training process and the rendering pipeline instead as the same as how we describe. Here, we take a deeper look on what is random patch sampling. As we described in the previous pipeline, when training NeRF with super resolution, we have to take a patch of the input image in order to fit in the device memory. Unlike previous work using grilled patch sampling, which uniformly crop the images and fit into the pipeline one by one, we propose to use random patch sampling, which sample different regions of the image for each training iteration. And we empirically found this technique can improve PSNR for most of the case while staying very efficient. Okay, let's talk about the evaluation. First, we choose TensorRF as our backbone NeRF model, and we use EDSR as our SR model. Both of them can be replaced with other NeRF and SR model as our pipeline is model agnostics. With this setup, we train and evaluate on both synthetic and real-world forward-facing datasets. We train our model for 150 APODs, which means 150 random patches per training image. Here, we compare the quality and efficiency when training and rendering on the GPU. Now we show the results of LLFF dataset, which is the real-world forward-facing dataset. As we can see from the table, FastSR-NeRF achieved on par quality to the baseline TensorRF at the 2x and 4x SR rates. For the 8x, FastSR-NeRF will suffer a larger quality loss. For the efficiency with comparable quality, FastSR-NeRF takes 2 to 5x longer time to train compared to TensorRF due to the SR training overhead. However, it is 90x faster than the other SR-based NeRFs. For rendering time, FastSR-NeRF has up to 30x speed compared to TensorRF, and also outperform other SR-based NeRFs such as NeRF+SR and RF+SR-NeRF. For model size, FastSR-NeRF is up to 12.5 times smaller than TensorRF and is also smaller than RF+SR-NeRF. Again, FastSR-NeRF achieves this without the need for customized CUDA kernels. In addition to GPU, we also evaluate FastSR-NeRF on consumer-grade MacBook laptop with M1 Pro and M2 chip. As we can see, FastSR-NeRF takes about 22 and 15 hours to train for 2x and 4x SR rates, but only takes 15 and 4 seconds to render. These are roughly 10 times slower than TensorRF, but up to 11 times faster to render. In contrast, for mobile NeRF, although it can render very fast, it takes more than 15 days if we want to train it on the same MacBook device. With this comparison, FastSR-NeRF has a much tolerable training time while still having an improved rendering speed. We also showed the rendering results, and we can see FastSR-NeRF can generate images that are comparable visual quality to the TensorRF with just a slightly lower PSNR. Okay, to sum up our work, we designed FastSR-NeRF, which is a simple NeRF and super res pipeline that can improve NeRF's training and rendering speed on consumer devices. We propose random patch sampling as an efficient data augmentation technique to improve the training quality. FastSR-NeRF demonstrates up to 11 times faster rendering speed while having a comparable quality and tolerable training time on a consumer laptop. Thank you for your attention. Please find more results in our paper. Thank you.